Hello, and thank you for joining me today as we continue our discussion on gases and energy. Today we're going to talk about properties of gases and the gas laws that kind of go with them. So you're going to get some different terms today. Things you should be able to do when we get done with this lesson. You'll be able to convert between different pressure units of a gas. You'll also be able to explain the relationship between pressure, volume, and temperature as they apply to a certain gas sample. And you'll be able to use the combined gas law equation to calculate an unknown variable. So let's get started. So first, we're going to talk gases are different from solids and liquids, and they fill whatever container they are occupying. So they fill the space. They have no definite shape, no definite volume. They're a fluid. They move past one another, extremely low densities, and they can be compressed. And this is kind of the piece here. This compression we call pressure. So this amount that they can be compressed we call pressure. And this is measured by a barometer. We use pressure all the time, especially with weather systems. They talk about low pressure, high pressure. That's talking this atmospheric pressure. 1 atmosphere is the pressure exerted by the air above you at sea level. And some other units we're going to use. 1 atmosphere is the same as 760 torr, which is also the same as 760 millimeters of mercury. We're going to get a couple more on the next slide, and we're going to talk about this. To do pressure conversions, though, and any sort of gas conversions, your temperature has to be in Kelvin. So this Kelvin equals Celsius plus 273 is going to be really important. And then the amount of gas is given in N. That's looking at the moles of gas there, which we'll talk about later on. Okay, so your pressure. Pressure is a force exerted over a certain area. And atmospheric pressure is the pressure applied downward by air molecules. Again, 1 atmosphere is the same as 760 torr, is the same as 760 millimeters of mercury. I don't know why they're the same, different names, same number. I don't know. That's the same as 101.325 kilopascals or 101,325 regular pascals. You will need to be able to convert between all of these different units. Again, to do these conversions, your temperature has to be in Kelvin. So to go from Kelvin to Celsius, you take Celsius, or from Celsius to Kelvin, you take Celsius plus 273 to get to Kelvin. And your standard temperature, if we talk standard temperature and pressure, STP, standard temperature is 273 Kelvin or 0 degrees Celsius and 1 atmosphere. These are really important numbers. You'll need to know these. So if I say something is at STP, you need to know that that means standard temperature and standard pressure, which is 0 degrees Celsius and 1 atmosphere, or 273 Kelvin and 1 atmosphere. All right. Some practice. A sample of neon gas has a pressure of 0.50 atmospheres. Give the pressure of the neon in millimeters of mercury, torr, pascals, and kilopascals. I will do the millimeters of mercury and torr with you, and you can do the rest on your own. And same with the bottom one. So water vapor has a pressure of 900 millimeters of mercury. Give the pressure in torr, atmospheres, pascals, so on and so forth. So for starters, we have 0.5 atmospheres. And I know that in 1 atmosphere, I have 760 millimeters of mercury. So I'm going to take 0.5 times 760 divided by 1. If I take 0.5 times 760, I should get 380 millimeters of mercury. And so you can do the same thing. That'll be the same answer for torr because those are the same. You'll have to use pascals and kilopascals. So remember, pascals is 101,325. Kilopascals is 101.325. So just 1,000 places difference. And the bottom one, a sample of water vapor has a pressure of 900 millimeters of mercury. Give the pressure in torr, atmospheres, pascals, and kilopascals. I'll do atmospheres for you so you can see this. So we have 900 millimeters of mercury. I know that I'm going to atmosphere. So I know that 1 atmosphere is the same as 760 millimeters of mercury. So in this case, I'm going to take my 900 and divide it by 760. And when I do that, I should get 1.1 0.18 atmospheres. So if you want to take a second and do the rest of these, I have answers on the next slide. So pause this screen, work through these, and I will join you when you get to the next slide. All right, here are your answers to those questions, those conversions. So you have your different conversions here, your different pressures. If you got answers different than mine, please come see me, talk to me, check yourself, walk through yourself again. I can walk through mine. Nobody says I did it right all the time. And we will do some more practice here in class and as we move forward. All right, so along with pressure conversions, we have different phases of matter, different gas laws. So there are 3 gas laws that we're going to combine when all is said and done. The first one is called Boyle's law. And just to be upfront and honest with you, I don't care that you know each one individually. I don't care that you know Boyle's law is that temperature stays the same. That's not important to me. I care that you can use the equation, you understand the relationships. Okay, so Boyle's law states that the volume of gas is inversely related to the pressure at a constant temperature, which means that as pressure goes up, volume goes down. If pressure goes down, volume goes up. And so these are connected by multiplication. So if you take your first pressure, P1, times your first volume times V1, and you change one of those, you're going to get a second pressure, which is going to create a second volume. For example, a sample of oxygen gas has a volume of 150 milliliters when its pressure is 0.947 atmospheres. What will the volume of the gas be at a pressure of 0.987 atmospheres if the temperature remains constant? In this case, you can leave your volume as milliliters. Because we're doing a ratio, we're doing a conversion on both sides, it's going to be the same on both sides, you're going to be fine. So you can leave it as milliliters. But work through this. When you do that, you should get an answer of 144 milliliters. If you're not getting that answer, again, please come see me, send me an email, let me know, and we'll figure out where we're going wrong at. Another guy named Charles, he found that the volume of a fixed mass of gas at a constant pressure varies directly with the temperature in Kelvin. This one's really important. Temperature has to be in Kelvin. If you're in Celsius, you're going to get some wacky numbers. Okay, so he found that the volume varies directly with temperature. So if volume goes up, my temperature also goes up. And to do this, we have to have an inverse relationship. Or a direct relationship. We have to have a division situation, where this is like a ratio. So my ratio here is going to stay the same. Okay, so I have volume over temperature equals volume over temperature. Remember, temperature has to be in Kelvin. Volume can be in milliliters or liters. That is irrelevant at this point. So here's your practice question. A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 degrees Celsius if the pressure remains constant? Work through this. Hopefully your answer matches mine at 815 milliliters. If it doesn't, let me know. Chat with me. We'll figure out where we deviated on this. On the last one, this is Guy-Lassac. His law. He found that the pressure of a fixed mass of gas at a constant volume varies directly with the temperature. So the last one, Charles, was volume over temperature. Guy-Lassac is pressure over temperature. So this is Guy-Lassac's. That pressure and temperature vary directly. So again, if this one goes up, your temperature also has to go up in order to make these two the same. Okay? So the gas in an aerosol can is at a pressure of 3.0 atmospheres at 25 degrees Celsius. Directions on the can. Warn the user not to keep the can in a place where the temperature exceeds 52 degrees Celsius. What would the pressure be in the can at 52 degrees Celsius? Remember, your temperature needs to be in Kelvin before you do the calculation. But I came to 3.27. Please let me know if you get something other than that. We can talk through it and figure out where we're going with everything. All right, and then the last situation. We have what's called a combined gas law, in which you can combine all 3 of those gas laws into one equation. So remember, Boyle said that pressure and volume vary indirectly. Charles said that volume and temperature and Guy Lasek said that pressure and temperature. Ooh. Those vary directly. So we can combine these. So we take all these and put them together, and you get P1 V1 over T1 equals P2 V2 over T2. This is the equation we're going to use a lot, and we can solve for any one of these variables. So here is an example. I have a gas at a pressure of 12 atmospheres, a volume of 23 liters, and a temperature of 200 Kelvin. If I raise the pressure to 14 atmospheres, increase the temperature to 300 Kelvin, what volume does my gas now occupy? So I have P1, V1, T1, and I have P2, V2, and T2. So my initial pressure was 12 atmospheres. So I'm going to put 12 atmospheres here. I know that my volume was 23 liters, and my temperature was 200 Kelvin. My second pressure was 14 atmospheres. The temperature was 300 Kelvin, and I'm looking for this. So I know that P1 V1 over T1 equals P2 V2 over T2, and I'm going to put my numbers in. So I'm going to have 12 atmospheres times 23 liters divided by 200 Kelvin equals 14 atmospheres times V2 over 300 Kelvin. And then I'm going to do a bunch of number crunching. So I'm going to take 12 times 23 divided by 200. I'm going to multiply that by 300 and divide by 14. And I came to an answer of V2 being equal to 29.6, or let's go 30 with a decimal liters for the sake of significant digits. Okay, so work through that, see what you come up with for an answer, and see if we get the same answer on that. All right, here are some review questions for you to try. Here's your first set. So first one's pressure conversions, and then you're going to practice your gas laws on the next three. Pause this screen. I have one more set of questions, so pause this, work through these, and then you can try this next set. So again, here's your last set of questions. Pause the screen, work through these questions, make sure you're comfortable answering them, and I will reconnect with you when we return to class. But thank you for your efforts and energy. I look forward to finishing up this unit with you.